Good day to all of you. So we're going to start our lecture series regarding computer organization and architecture. So I'll be basing my reference to William Stallings' book, The Computer Organization and Architecture 10th edition. And then these are the slides for this book. So I am not in any way the owner of this presentation, and I'll be using this as a video presentation. So I hope that after this lecture series, you will have an ample knowledge that you're going to apply with regards to computer organization and architecture. So let's start. So we have this, our first chapter is chapter 1, Basic Concepts and Computer Evolution. So in a class of computers called microcomputers, the relationship between architecture and organization is very close. Changes in technology not only influence organization, but also result in the introduction of more powerful and more complex architectures. Generally, there is less of a requirement for generation to generation compatibility for these smaller machines. Thus, there is more interplay between organizational and architectural design decisions. An intriguing example of this is the Reduced Instruction Set Computer, or the RISC, or the RISC, which we'll also be tackling in Chapter 15. So this lecture series examines both computer organization and computer architecture. The emphasis is perhaps more on the side of organization. However, because a computer organization must be designed to implement a particular architectural specification, a thorough treatment of organization requires a detailed examination of architecture as well. So let's get to the next slide to have a better understanding of computer architecture and computer organization. So based on this figure, so in describing computers, a distinction is often made between computer architecture and computer organization. Although it is difficult to give precise definitions for these terms, a consensus exists about the general areas covered, and an interesting alternate view is presented. So the definition for computer architecture, it refers to those attributes of a system visible to a programmer, or put another way, those attributes that have a direct impact on the logical execution of a program. A term that is often used interchangeably with computer architecture is the instruction set architecture, or the ISA. So the ISA defines instruction formats, instruction opcodes, registers, instruction, and data memory. The effect of executed instructions on the registers and memory, and an algorithm for controlling instruction execution. Then another one, the definition for computer organization, it refers to the operational units and their interconnections that realize the architectural specifications. Examples of architectural attributes include, so instruction set, the number of bits used to represent various data types such as numbers, characters, the input-output mechanisms, and techniques for addressing memory. So we can actually associate architecture attributes or computer architecture to software. And then organizational attributes include those hardware details transparent to the programmer, such as control signals, interfaces between the computer and peripherals, and the memory technology used. So obviously, in organizational attributes, they are more on the side of the hardware. So, to further understand the relationship between computer architecture and organization, so for example, it is an architectural design issue whether a computer will have a multiply instruction. Since multiply instruction is a type of an instruction set, it is, on the other hand, an organizational issue whether that instruction will be implemented by a special multiply unit or by a mechanism that makes repeated use of the add unit of the system. The organizational decision may be based on the anticipated frequency of use of the multiply instruction, the relative speed of the two approaches, and the cost and physical size of a special multiply unit. So, by this example, it is really pointed out that architecture is more on the side of the software details, while our computer organization is more on the hardware details. So historically and still today, The distinction between architecture and organization has been an important one. Many computer manufacturers offer a family of computer models, all with the same architecture, but with differences and organization. So it is evident if you're in malls, we have these laptops, they are all the same family models, but why does these prices vary? We have a more expensive laptop than a more affordable laptop. So let's continue. So consequently, the different models in the family have different price and performance characteristics. Of course, the more expensive the laptop is, of course, the more it's performing than those more affordable laptops. So furthermore, a particular architecture may span many years and encompass a number of different computer models, its organization changing with changing technology. So we have the first example for computer organization and architecture that really illustrates the relationship. So next is we have the IBM system, the 370 architecture. So this is a prominent example of this phenomena. So we have the IBM System 370 architecture. So this architecture was first introduced in 1970 and included a number of models. The customer with modest requirements could buy a cheaper, slower model, and if demand increased, later upgrade to a more expensive, faster model without having to abandon software that had already been developed. Over the years, IBM has introduced many new models with improved technology to replace older models, offering the customer greater speed, lower cost, or both. These newer models retain the same architecture so that the customer's software investment was protected. Remarkably, the System 370 architecture, with a few enhancements, has survived to this day as the architecture of IBM's mainframe product line. So that's I've been trying to explain that this family models of computers or laptops, they're using the same architecture, but it always boils down to the computer organization. So that's why more higher performing laptops, they are more expensive because they have more complex computer organization than the laptops which is a mid-range or has a lower price. So next, we have structure and function. So, a computer is a complex system. Contemporary computers contain millions of elementary electronic components. How then can one clearly describe them? So, the key to recognize the hierarchical nature of most complex system, so including this so-called computer. A hierarchical system is a set of interrelated subsystems, each of the latter in turn hierarchical in structure until we reach some lowest level of elementary subsystem. The hierarchical nature of complex system is essential to both their design and description. The designer need only to deal with particular level of a system at a time. At each level, the system consists of a set of components and their interrelationships. The behavior at each level depends only on a simplified, abstracted characterization of the system at the next lower level. At each level, the designer is concerned with structure and function. So the definition of structure is the way in which the components are interrelated. And then for the definition of function, the operation of each individual component as part of the structure. In terms of description, we have two choices, starting at the bottom and building up to a complete description, or the opposite, beginning with the top view and decomposing the system into its subparts. Evidence from a number of fields suggests that top-down approach is the clearest and most effective. So top-down approach is like general to specific. So the approach taken in this lesson follows from this viewpoint. The computer system will be described from the top down. So from a more whole picture of a computer, and then it will be decomposed into parts. So we begin with the major components of a computer, describing their structure and function, and proceed to successively lower layers of the hierarchy. The remainder of this section provides a very brief overview of this plan of attack. So next is we have dedicated for the function. So function, so both structure and functioning of a computer are in essence simple. So in the next presentation, we have figure 1.1 depicts the basic functions that a computer can perform. In general terms, there are only four. So we have data processing. The data may take a wide variety of forms, and the range of processing requirements is broad. However, we shall see that there are only a few fundamental methods or types of data processing. Next is we have data storage. Even if the computer is processing data on the fly or data come in and get processed and the results go out immediately, the computer must temporarily store at least those pieces of data that are being worked on at any given moment. Thus, there is at least a short-term data storage function. Equally important, the computer performs a long-term data storage function. Files of data are stored on the computer for subsequent retrieval and update. So for data storage, the short term is like you're storing data in the random access memory. That's why RAM is also called a volatile memory because once the power is cut off from supplying the RAM, the data will dissipate or evaporated for the term. And then for the long term is the very good example is the data that you saved in your USB flash drive or on your hard disk drives of your computer. So that's the example of long term. Okay, next is we have the data movement. The computer's operating environment consists of devices that serve as either sources or destinations of data. When data are received from or delivered to a device that is directly connected to the computer, the process is known as input-output, and the device is referred to as a peripheral. When data are moved over long distances to or from a remote device, the process is known as data communications. So to further understand, if your hard drive is connected to your, of course, to your in the computer system, so it can also be referred as a peripheral. While if you're going to send your data through the network, that is already an example of data communications. Next is we have control. Within the computer, a control unit manages the computer's resources and orchestrates the performance of its functional parts in response to those instructions. So as I have already mentioned figure 1.1, so the next slide, so we have this figure 1.1, which is a top-down view of a computer. So we now look in a general way at the internal structure of a computer. We begin with a traditional computer with a single processor. So this is the image, and then that employs a microprogrammed control unit. Then examine a typical multi-core structure. So figure 1.1 provides a hierarchical view of the internal structure, of course, of a traditional single processor computer. So this is an example of a top view approach. So we have a computer which has an I/O, main memory, and then system bus and CPU. And then we want to look for the components inside the central processing unit. So we're going to zoom in, and then we can see the parts of the CPU, which is composed of registers, um, arithmetic logic a unit, and we have the internal bus and control unit. And we also want to look for the contents or scrutinize the contents of the control unit. So we have what's inside the control unit is we have the sequencing logic, control unit, registers and decoders, and control memory. So this is a perfect example of a top-down approach. Okay, so next is we have there are four main structural components. So, first is we have the central processing unit or the CPU. Controls the operation of the computer and performs its data processing functions, often simply referred to as the processor. And then next is we have main memory, which stores data. Next is we have input output or I/O, moves data between the computer and its external environment. And then next is we have system interconnection, some mechanisms that provide for communication among CPU, main memory, and input-output or I/O. A common example of a system interconnection is by means of a system bus, consisting of a number of conducting wires to which all the other components are attached. And then next is we have, how about the CPU major structural components? So there may be one or more of each of the aforementioned components. Traditionally, there has been just a single processor. In recent years, there has been increasing use of multiple processors in a single computer. Some design issues relating to multiple processors crop up and are discussed as the text proceeds. So part 5 of this lecture series focuses on such computers. So each of these components will be examined in some detail in part 2. However, for our purposes, the most interesting and in some ways the most complex component is the CPU or the Central Processing Unit. Its major structural components are as follows. So we have the control unit, controls the operation of the CPU and hence the computer. Next is we have the arithmetic and logic unit or the ALU or the ALU, performs the computer's data processing functions. Next is we have the registers, provides storage internal to the CPU. And we also have the CPU interconnection, some mechanisms that provide for communication among the control unit, the ALU, and registers. So part 3 covers these components where we will see that complexity is added by the use of parallel and pipelined organizational techniques. Finally, there are several approaches to the implementation of the control unit. A common approach is a microprogrammed implementation. In essence, a microprogram control unit operates by executing micro instructions that define the functionality of the control unit. With this approach, the structure of the control unit can be depicted as in figure 1.1, and this structure is also examined in part 4. So next is we have multi-core computer structure. As was mentioned, contemporary computers generally have multiple processors. When these processors reside on a single chip, the term multi-core computer is used, and each processing unit, which is consisting of control unit, the ALU, registers, and perhaps a cache, is called a core. To clarify the terminology, this text will use the following definitions. So first is we have the central processing unit again, or the CPU, that portion of a computer that fetches and executes instructions. It consists of an ALU, a control unit, and registers. In a system with a single processing unit, it is often simply referred to as a processor. So please change your mindset or your description that actually central processing unit, it refers to the microprocessor or the processor. Do not make it that it is the system unit or the which houses the motherboard, disk drives, your other peripherals that is connected to the computer. That is called the system unit. It's not called as the central processing unit because again, CPU refers to the processor and the microprocessor itself. So next is another definition is we have the core, an individual processing unit on a processor chip. A core may be equivalent in functionality to a CPU on a single CPU system. Other specialized processing units, such as one optimized for vector and matrix operation, are also referred to as cores. So you can imagine cores as in a real world situation as the brain. So the brain that is in our head, example. So for that example, we have a single core. So what is the meaning of if you have quad core or octa-core? So for octa-core, for instance, it means you have 8 brains inside your head. That's the representation of a core if you're going to relate it in a real life situation. Physically, you have one. In our example, physically you have one head, but inside of you have 8 brains. So that's the notion for an octa-core. Next is we have processor, a physical piece of silicon containing one or more cores. The processor is the computer component that interprets and executes instructions. If a processor contains multiple cores, it is referred to as a multi-core processor. After about a decade of discussion, there is a broad industry consensus on this usage. So, for a processor, this is the physical, the one that we're seeing, the chip. But you can never know that inside a processor, there are one or more cores. Okay, next is we have the cache memory. So another prominent feature contemporary computers is the use of multiple layers of memory called cache memory between the processor and the main memory. So chapter 4 is devoted to the topic of cache memory. For our purposes in this section, we simply note that a cache memory is smaller and faster than main memory and is used to speed up memory access by placing in the cache data from main memory that is likely to be used in the near future. So that is the purpose of cache memory. It is faster because it's smaller. It has a smaller capacity than main memory, and cache memory is already housed with the processor. So that's why putting data inside your cache memory will be faster in execution because it's already available for the processor to work on than you're going to fetch it to the main memory in which it will still go with the it will be going to the system bus. So that's why it's the travel time of the data from main memory to the processor will also count. So that's why it is slow. It is slower. Okay, then also we have a greater performance improvement may be obtained by using multiple levels of cache. So we have level 1 or L1 closest to the core and additional levels L2, L3, and so on, progressively farther from the core. But still, this L1, L2, L3 is inside your processor. So in this scheme, level n is smaller and faster than level n plus 1. So by means of our example, L1, L2, L3, L1 is the smallest and the fastest among L1, L2, and L3 based on this statement. Okay, we next is we are going to have an illustration of a cache memory. So we have this our motherboard. It's in general. So we have our processor chip. This is the top view again approach. And then inside the processor chip is we have a number of cores. So this one, two, three, four. We have an octa-core, and then we have two L3 caches. And then we want to see what's inside a core. And then if we break down and look into it, zoom into it, so we have these parts of the core. So we have the instruction logic, the arithmetic and logic unit or the ALU, and the load or store logic. And then we have the L1 iCache and L2 data cache. So L1 is for instruction, and then another L1 is for data. And then we have L2 instruction cache and L2 data cache. So this figure is a simplified view of the principal components of a typical multi-core computer. Most computers, including embedded computers in smartphones and tablets, plus personal computers, laptops, and workstations, are housed on a motherboard, as I've said. Before describing this arrangement, we need to define terms. So a printed circuit board, or PCB, is a rigid, flat board that holds and interconnects chips and other electronic components. The board is made of layers, typically 2 to 10, that interconnect components via copper pathways that are etched into the board. So the main printed circuit board in a computer is called a system board or motherboard, the biggest PCB, while smaller ones that plugged into slots in the main board are called expansion boards. So the most prominent elements on the motherboard are the chips. A chip is a single piece of semiconducting material, typically silicon, upon which electronic circuits and logic gates are fabricated. The resulting product is referred to as an integrated circuit or IC. The motherboard contains a slot or socket for the processor chip, as we can see in the figure, which typically contains multiple individual cores in what is known as a multi-core processor, as you can see with our processor chip here, if you zoom in for the processor chip. There are also slots for memory chips, I/O controller chips, and other key computer components. For desktop computers, expansion slots enable the inclusion of more components on expansion boards because, of course, desktop computers are better for upgrade or updating hardware because it that is housed with a system unit. You can change it easier compared to a laptop. Which laptops you have a limited upgrade such as the hardware and memory. And then next is thus a modern motherboard connects only a few individual chip components, with each chip containing from a few thousand up to hundreds of millions of transistors. So this figure shows a processor chip that contains 8 cores. So we have in our processor chip and an L3 cache. Not shown is the logic required to control the operations between the cores and the cache and between the cores and the external circuitry on the motherboard. The figure indicates that the L3 cache occupies two distinct portions of the chip surface. However, typically all cores have access to the entire L3 cache via the aforementioned control circuits. The processor chip shown in this figure does not represent any specific product but provides a general idea of how such chips are laid out. And then next, we zoom in on the structure of a single core, which occupies a portion of a processor chip. In general terms, the functional elements of a core are, first is we have instruction logic. So this includes the tasks involved in fetching instructions and decoding each instruction to determine the instruction operation and the memory locations of any operands. Next is we have the arithmetic logic unit or the ALU performs the operation specified by an instruction. Next is we have the load store logic manages the transfer of data to and from main memory via cache. And then the core also contains an L1 cache split between an instruction cache or the I cache that is used for the transfer of instructions to and from main memory. And then we also have the L1 data cache for the transfer of operands and results. Typically, today's processor chips also include an L2 cache as part of the core. So we have this L2 caches. In many cases, this cache is also split between instruction and data caches, although a combined single L2 cache is also used. So it depends upon the manufacturer of the processor. Keep in mind that this representation of the layout of the core is only intended to give a general idea of the internal core structure. In a given product, the functional elements may not be laid out as the three distinct elements as shown in this figure, especially if some or all of these functions are implemented as part of the microprogrammed unit. As I've said, the organization depends upon the model of the processor. Okay, and then as you can see that it is said here that which is the smallest and the fastest cache, it is L1. And then of course, among the caches, L3 is the slowest and biggest because slowest because it's outside of the core. And of course, it's always been the standard that L1 cache is the smallest and the fastest. Okay, next is we have an illustration of, for figure 1.3, the motherboard with two Intel quad-core Xeon processors. So how will you know that it has um, two processors? Because, of course, processors require a CPU fan. So that's why it has two fans. So it really requires, because of course, processors dissipates heat, so it needs to dissipates heat easily. Because if not, our processors will overheat, and of course, it will be rendered useless. So it will be instructive to look at some real-world examples that illustrate the hierarchical structure of computers. So figure 1.3 is a photograph of the motherboard. So this is the motherboard of for a computer built around for two Intel quad-core Xeon processor chips. So these are the two processors with the CPU fan. Many of the elements labeled on the photograph are discussed subsequently in our lecture series. Here we mention the most important in addition to the processor sockets. So let's deal with some of its parts. So PCI Express slots for a high-end displayed adapter for additional peripherals. It is also described as, in short, PCIe. And then next is we have Ethernet controller and Ethernet ports for network connections, USB sockets for peripheral devices such as mouse, keyboard, and also your flash drives and sometimes your hard drives. And then we have serial ATA or SATA sockets for connection to disk memory. So the section 7.7 discusses the Ethernet, USB, and the SATA. And then interfaces for DDR or the double data rate main memory. So DDR is also discussed in section 5.3. And then Intel 3420 chipset is an I/O microcontroller for direct memory access operations between peripheral devices and main memory. And then 7.5 discusses all about the DDR and the input-output controller. So we have another figure next is all about figure 1.4, the Z Enterprise EC12 processor unit chip diagram. Again, following our top-down strategy as is illustrated in figures 1.1 and 1.2, we can now zoom in and look at the internal structure of a processor chip. For variety, we look at an IBM chip instead of the Intel processor chip. So this figure is a photograph of the processor chip for the IBM Z Enterprise EC12 mainframe computer. So this chip has 2.75 billion transistors. The superimposed labels indicate how the silicon real estate of the chip is allocated. As we can see, the chip has 6 cores, 1, 2, 3, 4, 5, 6, or processors. In addition, there are two large areas labeled L3 cache. So 1, 2, 3. As I've said, the computer organization or specifically for processor, it depends upon the processor manufacturer. Okay, so um, we have for L3 caches, which are shared by all 6 processors. So the L3 controls traffic between the L3 cache and the cores between the L3 cache and the external environment. Additionally, there is storage control or SC logic between the cores and the L3 cache. So that's why we have this SC. The memory controller or the MC function controls access to memory external to the chip. So we have this MC. And then the GXIO bus controls the interface to the channel adapters accessing the IO. So we have this IO here and the GXIO specific. Okay, so this is the Z Enterprise EC12 processor chip diagram. So next is another figure. Figure 1.5, so the Z Enterprise EC12 core layout. So going down one level deeper, we examine the internal structure of a single core. So, from the 6 cores, we zoomed in, as shown in the photograph of this figure. So keep in mind that is a portion of the silicon surface area making up a single processor chip. The main sub-areas within this core area are the following. We have the ISU, or the instruction sequence unit, determines the sequence in which the instructions are executed in what is referred to as a superscalar architecture. So we have this ISU. Then next is we have the IFU, or the instruction fetch unit, logic for fetching instruction, the IFU. Next is we have the IDU, or the instruction decode unit. So the IDU is fed from the IFU buffers and is responsible for the parsing and decoding of all Z architecture operation codes. So we have the IDU. And then we have the LSU, or the load store unit. So the LSU contains the 96 kilobyte L1 data cache and manages data traffic between the L2 data cache and the functional execution unit. It is responsible for handling all types of operand accesses of all lengths, modes, and formats as defined in the Z architecture. So we have this LSU. And then we have the XU, or the translation unit. So this unit translates logical addresses from instructions into physical addresses in main memory. The XU also contains a translation look-aside buffer, or TLB, used to speed up memory access. So TLBs are discussed in chapter 8 of our lecture series. So this is the XU, or the translation unit. Next is we have the FXU, or the fixed point unit. The FXU executes fixed point arithmetic operations. Okay, the FXU. And then next is we have the BFU, or the binary floating point unit. The BFU handles all binary and hexadecimal floating point operations as well as fixed point multiplication operations, the BFU. Next is we have the DFU, or the decimal floating point unit. So we have this one, DFU. The DFU handles both fixed point and floating point operations on numbers that are stored as decimal digits. And then next is we have the RU, or the recovery unit. The RU keeps a copy of the complete state of the system that includes all registers, collects hardware fault signals, and manages the hardware recovery actions. The RU, or the recovery unit. Next is we have the COP, or the dedicated coprocessor. The COP is responsible for data compression and encryption functions for each core, the COP, or the coprocessor. And then we have also the iCache. This is a 64 kilobyte L1 instruction cache, allowing the IFU to prefetch instructions before they are needed, the iCache. And then next is the L2 control. This is the control logic that manages the traffic through the two L2 caches. So L2 control. Next is we have data L2. So it is a 1 megabyte L2 cache, L2 data cache for all memory traffic and other than the instructions. So 1 megabyte. So maybe that's why it's bigger compared to the others. And then we have also the instruction L2 a 1 megabyte L2 instruction cache. So it's the same size with capacity in terms of capacity with the data L2 cache. So these are the parts of the let's go back. These are the parts of the Z Enterprise EC12 core layout. So I hope that you remember the parts. Next is we have, let's deal with the history of computers. So we have this first generation. So the first generation of computers used vacuum tubes for digital logic elements and memory. A number of research and then commercial computers were built using vacuum tubes. For our purposes, it will be instructive to examine perhaps the most famous first generation computer known as the IAS computer. So IAS stands for Institute for Advanced Studies. So a fundamental design approach for first implemented in the IAS computer is known as the stored program concept. This idea is usually attributed to the mathematician John von Neumann. So it is spoken as or pronounced as, it's not von Neumann, it's John von Neumann. So Alan Turing developed the idea at about the same time. So the first publication of the idea was in a 1945 proposal by von Neumann for a new computer, the EDVAC, or the Electronic Discrete Variable Computer. In 1946, von Neumann and his colleagues began the design of a new stored program computer, referred to as the IAS computer, at the Princeton Institute for Advanced Studies, in which the IAS acronym gets its name from the Princeton Institute for Advanced Studies. So the IAS computer, although not completed until 1952, is the prototype of all subsequent general purpose computers. Okay, next, as you can see in our figure 1.6, it shows the general structure of the IAS computer. And let's compare it with, as you can remember, with figure 1.1. So it consists of a main memory, just the same, which stores both data and instructions. Next is also it has an arithmetic logic unit, or the ALU, capable of operating on binary data. And then next is we have a control unit, which interprets the instructions in memory and causes them to be executed. Next is we have also the input-output, or the IO equipment operated by the control unit. So this structure was outlined in von Neumann's earlier proposal, which is worth quoting in this part at this point. And then next is first, since the device is primarily a computer, as we can already see, it has the same components as with the typical computers that we have now. It will have to perform the elementary operations of arithmetic most frequently. These are the addition, subtraction, multiplication, and division. It is therefore reasonable that it should contain specialized organs for these operations. It must be observed, however, that while this principle as such is probably sound, the specific way in which it is realized requires close scrutiny. At any rate, a central arithmetical part of the device will probably have to exist, and this constitutes to the first specific part, the CA. So CA refers to central arithmetic. So next, or second, the logical control of the device, that is, the proper sequencing of its operations, can be most efficiently carried out by a central control organ. If the device is to be elastic, that is, as nearly as possible all-purpose, then a distinction must be made between the specific instructions given for and defining a particular problem, and the general control organs that see to it that these instructions, no matter what they are carried out. The former must be stored in some way. The latter are represented by definite operating parts of the device. By the central control, we means this latter function only, and the organs that performed it form the specific part, which is the second specific part, the CC or the central control. Third, any device that is carried out long and complicated sequences of operations, specifically of calculations, must have a considerable memory. The instructions which govern a complicated problem may constitute a considerable material, particularly so if the code is circumstantial, which it is in most arrangements. So this material must be remembered. So at any rate, the total memory constitutes the third specific part of the device, which is M. M, of course, stands for memory. And then next, the three specific parts, as mentioned, the CC and CA is collectively called as C, and M correspond to the associative neurons in the human nervous system, if we're going to compare it to our nervous system. It remains to discuss the equivalence of the sensory or the afferent and the motor or the efferent neurons. These are the input and output organs of the device. So the device must be endowed with the ability to maintain input and output, which is sensory and motor contact with some specific medium of this type. As we can see, sensory is the input and motor is the output. So this medium will be called the outside recording medium of the device, or R. So R stands for recording. Next, or fourth, the device must have organs to transfer information from R into its specific parts C and M. So these organs form its input. The fourth specific part I, so I is refers to input. It will be seen that it is best to make all transfers from R by I into M and never directly from C. And then fifth, the device must have organs to transfer from its specific part C and M into R. These organs forms its output, the fifth specific part, O, which is again output. It will be seen that it is again the best to make all transfers from M by O into R and never directly from C. So that is the explanation for figure 1.6, the IAS structure. So next is we have another figure, which is the Ias Memory Formats. With rare exceptions, all of today's computers have this same general structure and function and are thus referred to as the von Neumann machines. Thus, it is worthwhile at this point to describe briefly the operations of the Ias computer. So following this, the terminology and notation of the von Neumann rather, are changed in the following to conform more closely to modern usage. The examples accompanying this discussion are based on the latter text. So the memory of the IAS consists of the 4096 storage locations, called words, of 40 binary digits or bits each. Both data and instructions are stored there. And then numbers are represented in binary form. So it means binary, you're only using two numbers, which is 0 and 1. So that's why we can already imagine that the data of computer is only composed of zeros and ones. And each instruction is a binary code. So this figure illustrates these formats. So each number is represented by a sign bit. So we have the sign bit here, 1 bit for the sign bit, and a 39-bit value. So 39 plus 1 is equal to 40-bit. And then a word may alternatively contain two 20-bit instructions, with each instruction consisting of an 8-bit operation code or opcode specifying the operation to be performed, and 12-bit address designating one of the words in memory, numbered from 0 to 999. So that's all for the Ias memory formats. Next is we're going to deal with registers. So registers, so the control unit operates the IAS by fetching instructions from memory and executing them one at a time. We explain these operations with reference to figure 1.6. So this figure reveals that both the control unit and the ALU contain storage locations called registers defined as follows. So these are the types of registers. We have the memory buffer register, or the MBR. Contains a word to be stored in memory or sent to the I/O unit, or is used to receive a word from memory or from the I/O unit. Next is we have the memory address register, or the MAR. It specifies the address in memory of the word to be written from or read into the MBR. Next is we have the instruction register, or IR. Contains the 8-bit opcode instruction being executed. Next is we have the instruction buffer register, or the IBR, employed to hold temporarily the right-hand instruction from a word in memory. Next is we have program counter, contains the address of the next instruction pair to be fetched from memory. And next is we have the accumulator, or AC, and the multiplier quotient, MQ, employed to hold temporarily operands and results of ALU operations. For example, the result of multiplying two 40-bit numbers is an 80-bit number. The most significant 40 bits are stored in the AC and the least significant in the MQ. So these are the types of registers that can be found in our compute rather inside the control unit and the ALU. Okay, next is we have the figure 1.8, partial flow chart of the IAS operation. So to understand the flow, so the IAS operates by repetitively performing an instruction cycle as shown in this figure. Each instruction cycle consists of two subcycles, which is the fetch cycle. First is the fetch cycle, and then next is we have the execution cycle. The opcode of the next instruction is loaded into the IR, and the address portion is loaded into the MAR. So this instruction may be taken from the IBR, or it can be obtained from memory by loading a word into the MBR and then down to the IBR, IR, and MAR. Why the indirection? So these operations are controlled by electronic circuitry and result in the use of data paths. To simplify the electronics, there is only one register that is used to specify the address in memory for a read or write, and only one register used for the source or destination. Once the opcode is in the IR, the execute cycle, so the other one, is performed. Control circuitry interprets the opcode and executes the instruction by sending out the appropriate control signals to cause data to be moved or an operation to be performed by the ALU. Okay, so that's all for the partial flow chart of the IAS operation. So it is composed of fetch and execution cycle. So next is we have here a table of the Ias instruction set. So the Ias computer had a total of 21 instructions, which are listed in this table. So this can be grouped as follows. So first group of this 21 instruction is the data transfer. Move data between memory and ALU registers or between the two ALU register. Next is we have the unconditional branch. Normally, the control unit executes the instructions in sequence from memory. This sequence can be changed by a branch instruction, which facilitates repetitive operations. If we have unconditional branch, we also have conditional branch. The branch can be made dependent on a condition, thus allowing decision points. So, to further understand these branches, um, you can understand it if you studied computer programming. Next is we have arithmetic, operations performed by the ALU. And then next is we have address modify, permits addresses to be computed in the ALU and then inserted into instructions stored in memory. This allows a program considerable addressing flexibility. So this table present instructions in a symbolic, easy to read form. Actually, each instruction must conform to the format of figure 1.7b. So the opcode portion or the first 8 bits specify which of the 21 instruction is to be executed. The address portion, the remaining 12 bits, specify which of the 4096 memory location is to be involved in the execution of the instruction. So next, we are finished with the first generation from the history of computers. So let's deal with the second generation, which are the transistors. So the first major change in the electronic computer came with the replacement of the vacuum tube by the transistor. The transistor is smaller, cheaper, and dissipates less heat than a vacuum tube, but can be used in the same way as a vacuum tube to construct computers. So, because of this discovery, so it has a transistor has very many advantages, which is smaller, cheaper, and it dissipates less heat. And then, unlike the vacuum tubes, which requires wires, metal plates, a glass capsule, and a vacuum, so that's why transistors are cheaper. The transistor is a solid-state device made from silicon. So the transistor was invented at Bell Labs in 1947 and by the 1950s had launched an electronic revolution. It was not until the late 1950s, however, that fully transistorized computers were commercially available. The use of the transistor defines the second generation of computers. And then next is we have a table 1.2 of computer generations. So it has become widely accepted to classify computers into generations based on the fundamental hardware technology employed, as shown in table 1.2. Each new generation is characterized by greater processing performance, larger memory capacity, and smaller size than the previous one, as it is already evident in our time. So as we can see here, the first generation, the technology used is the vacuum tube, and then second generation is transistor. So third generation is by using the small and medium scale integration, the SSI and the MSI. And then the fourth generation is by using large scale integration or the LSI. And then the fifth generation is very large scale integration, which is the VLSI. And then the sixth generation from 1991 up to present is we have the ultra large scale integration or the ULSI. So as you can see also, um, as I've already mentioned, it has greater processing performance compared to its previous generation. Okay, next, let's continue the discussion of the second generation computers. So, but there are other changes as well. The second generation saw the introduction of more complex arithmetic and logic units and control units, the use of high-level programming languages, and the provision of system software with the computer. So, as you can see, since the computer organization has upgraded, it also affected the architecture. So, in broad terms, system software provided the ability to load programs, move data to the peripherals, and libraries to perform common computations, similar to what modern operating systems like Windows and Linux do. So next is we have figure 1.9, an IBM 7094 configuration. So let's see what is about this computer. So it will be useful to examine an important member of the second generation, the IBM 7094. From the introduction of the 700 series in 1952 to the introduction of the last member of the 7000 series in 1964, this IBM product line underwent an evolution that is typical of computer products. Successive members of the product line showed increased performance, increased capacity, and of course, lower cost. Also, over the lifetime of this series of computers, the relative speed of the CPU increased by a factor of 50. Speed improvements are achieved by improved electronics because, of course, from vacuum tubes, the second generation computer used a transistor implementation, which is faster than a vacuum tube implementation, and more complex in circuitry. For example, the IBM 7094 includes an instruction backup register used to buffer the next instruction. The control unit fetches two adjacent words from memory for an instruction fetch, except for the occurrence of branching instruction, which is relatively infrequent, or perhaps 10 to 15%, which happened. So this means that a control unit has to access memory for an instruction only half the instruction cycle. This prefetching significantly reduces the average instruction cycle time. And then figure 1.9 also shows a large or many peripherals configuration for an IBM 7094. As you can see, for the peripheral devices that is enumerated or shown here. And then several differences also for from the Ias computer are worth noting. So the most important of this is the use of data channels. As we can see, we have data channels here. So a data channel is an independent I/O module with its own processor and instruction set. In a computer system with such devices, the CPU does not execute detailed I/O instructions. Such instructions are stored in a main memory to be executed by a special purpose processor in the data channel itself. The CPU initiates an I/O transfer by sending a control signal to the data channel, instructing it to execute a sequence of instructions in memory. So the data channel also performs its task independently of the CPU and signals the CPU when the operation is complete. This arrangement relieves the CPU of a considerable processing burden. Another new feature of this second generation computer is the multiplexor, which is the central termination point for data channels, the CPU and memory. The multiplexer schedules access to the memory from the CPU and data channels, allowing these devices to act independently. So we are finished with the second generation. Next, we have the third generation. So the third generation is all about integrated circuits. A single self-contained transistor is called a discrete component. So why is it called discrete? Because it accepts fixed values. Specifically for discrete, it only has two values, 0 and 1. Throughout the 1950s and early 1960s, electronic equipment was composed largely of discrete components, such as transistors, resistors, capacitors, and so on. Discrete components were manufactured separately, packaged in their own containers, and soldered or wired together onto masonite-like circuit boards, which were then installed in computers, oscilloscopes, and other electronic equipment. Whenever an electronic device is called for a transistor, a little tube of metal containing a pinhead-sized piece of silicon had to be soldered to a circuit board. The entire manufacturing process, from transistor to circuit board, was expensive and cumbersome. So these facts of life were beginning to create problems in the computer industry. Early second generation computers contained about 10,000 transistors. This figure grew to the hundreds of thousands, making the manufacture of newer, more powerful machines increasingly difficult. So in 1958 came the achievement that revolutionized electronics and started the era of microelectronics, the invention of the integrated circuit, or the IC. It is the integrated circuit that defines the third generation of computers. So in this section, we provide a brief introduction to the technology of integrated circuits. Then we look at perhaps the most important members of the third generation, both of which were introduced at the beginning of that era. So the IBM System 360 and the DEC PDP 8. So let's look of the fundamental computer elements of the third generation computers. So in figure 1.10 is we have this computer elements, which is a gate and the memory cell. So microelectronic means literally micro means small, and then of course electronics is of electronics. Since the beginnings of digital electronics and the computer industry, there has been a persistent and consistent trend toward the reduction in size of digital electronic circuits. Before examining the implications and benefits of this trend, we need to say something about the nature of digital electronics. So a more detailed discussion is found in chapter 11 of this lecture series. So the basic elements of a digital computer, as we know, must perform storage, movement, processing, and control function. Only two fundamental types of components are required for these operations, as based in this figure are the gates and memory cells. So a gate, it is a device that implements a simple Boolean or logical function such as if A and B are true, then C is true, which is an AND gate. This is the description of the operation of the AND gate. So such devices are called gates because they control data flow in much the same way that canal gates control the flow of water. The memory cell, another element, is a device that can store one bit of data. That is, the device can be in two or of two stable states at any time. By interconnecting large number of these fundamental devices, we can construct a computer. So, further discussion of ICs or integrated circuits. So, we can relate this to our four basic functions as follows. First is data storage. It is provided by memory cells. Data processing. It is provided by gates. The data movement, the paths among components are used to move data from memory to memory and from memory through gates to memory. Next is we have the control. The paths among components can carry control signals. For example, a gate will have one or two data inputs plus a control signal input that activates the gate. When the control signal is on, the gate performs its functions on the data inputs and produces a data output. Similarly, the memory cell will store the bit that is on its input lead when the write control signal is on and will place the bit that it is in the cell on its output lead when the read control signal is on. Thus, a computer consists of gates, memory cells, and interconnections among these elements. The gates and memory cells are, in turn, constructed of simple digital electronic components. So the IC exploits the fact that such components as transistors, resistors, and conductors can be fabricated from a semiconductor such as silicon. It is merely an extension of the solid-state art to fabricate an entire circuit in a tiny piece of silicon rather than assemble discrete components made from separate pieces of silicon into the same circuit. So many transistors can be produced at the same time on a single wafer of silicon. Equally important, these transistors can be connected with the process of metallization to form circuits. So we can see the illustration in the next figure. So with figure 1.11, so we can see the relationship among the wafer, the chip, and the gate. The gate rather, this is the gate. And then this is the package chip, which is this green is the chip in which contains the a processor. And then on this processor, we have gates. So we have figure 1.11 rather, depicts the key concepts in an integrated circuit or IC. So a thin wafer, so this is the wafer, of silicon is divided into a matrix of small areas, each a few millimeters square. So this, few millimeters square. So this one. And then the identical circuit pattern is fabricated in each area, and the wafer is broken up into chips. So this chips is this one, and this is also here with a package chip with a pin. It's just the same. Okay. And then each chip consists of many gates and or memory cells plus a number of input and output attachment points. So this chip is then packaged in housing that protects it. So this is the package chip. And then inside, of course, the chip is we have the gate. And then And this housing protects it and provides pins for attachment to devices beyond, of course, the chip. And then a number of these packages can then be interconnected on a printed circuit board to produce larger and more complex circuit. So again, this is a top-down design. As you can see the relationship between the wafer, the chip, and the gate, and of course the package chip, in which this is already the one that is to be installed in our motherboard because it already has pins. Okay, next is we have another figure 1.12, a graph of growth in transistor count on integrated circuits. So because of this, initially only a few gates or memory cells could be reliably manufactured and packaged together. These early integrated circuits are referred to as small-scale integration, or SSI. As time went on, it became possible to pack more and more components on the same chip. This growth in density, as illustrated in the figure, so it is one of the most remarkable technological trends ever recorded, if you are familiar. So this figure reflects the famous Moore's Law, which was propounded by Gordon Moore, co-founder of Intel, in 1965. So Moore observed that the number of transistors that could be put on a single chip was doubling every year, and correctly predicted that this pace would continue into the near future. So that's why Moore's Law is very significant in the processor industry. To the surprise of many, including Moore, the pace continued year after year and decade after decade. The pace slowed to a doubling every 18 months. So it means that earlier, Moore observed it is year after year, but then it slowed, it began to have 18 months, or 1.5 years in the 1970s, but has sustained that rate ever since. Okay, so we have the Moore's Law. So, a further detail of Moore's Law. So, what is the consequences of Moore's Law? Which we can see and which is very profound. Number one, the cost of a chip has remained virtually unchanged during this period of rapid growth in density. This means that the cost of computer logic and memory circuitry has fallen at a dramatic rate. Next, because logic and memory elements are placed under which are placed closer together on more densely packed chips, the electrical path length is shortened, increasing operating speed. And then the third one, the computer becomes smaller, making it more convenient to place in a variety of environments. So you can see, because of Moore's law, if you're going to research example of devices such as our cell phones of our computer, if you're going to search those Jurassic devices at the 1970s or 1980s, you can see that the devices are very bulky compared to our devices that we are using today. So next is we have number 4. There is a reduction in power and cooling requirements. And then number 5, the interconnections on the integrated circuit are much more reliable than solder connections. With more circuitry on each chip, there are fewer inter-chip connections. Okay, next. So we have an example of the this third generation that uses the transistors. We have the IBM System 360. So by 1964, IBM had a firm grip on the computer market with its 7000 series of machines. In that year, IBM announced the System 360, a new family of computer products. Although the announcement itself was no surprise, it contained some unpleasant news for current IBM customers. The 360 product line was incompatible with older IBM machines, so it is backwards incompatible. So, thus, the transition to the 360 would be difficult for the current customer base, specifically if they own the older versions of IBM computers. So, this was a bold step by IBM, but one IBM felt was necessary to break out of some of the constraints of the 7000 architecture and to produce a system capable of evolving with the new integrated circuit technology. So the strategy paid off, both financially and technically. The 360 was the success of the decade and cemented IBM as the overwhelmingly dominant computer vendor with a market share above 70%. And with some modifications and extensions, the architecture of the 360 remains to this day the architecture of IBM's mainframe computers. Examples using this architecture can be found throughout the book of William Stallings. So the System 360 was the industry's first planned family of computers. The family covered a wide range of performance and cost. The models were compatible in the sense that a program written for one model should be capable of being executed by another model in the series, with only a difference in the time it takes to execute. So the System 360 is the one that started the trend of the family models of computers and laptops. So next, let's delve with the family characteristics of the IBM 360. So the concept of a family of compatible computers was both novel and extremely successful. A customer with modest requirements and a budget to match could start with a relatively inexpensive Model 30. Later, if the customer's needs grew, it was possible to upgrade to a faster machine with more memory without sacrificing the investment in already developed software. The characteristics of a family are as follows. So these are the six characteristics. First is similar or identical instruction set. In many cases, the exact same set of machine instruction is supported on all members of the family. Thus, a program that executes on one machine will also execute on any other. In some cases, the lower end of the family has an instruction set that is a subset of of the top end of the family. This means that programs can move up but not down. Second, similar or identical operating system. The same basic operating system is available for all family members. In some cases, additional features are added to the higher end members. Of course, additional features means the higher cost. Next is we have increasing speed. The rate of instruction execution increases in going from lower to higher family members, obviously. And then next is we have increasing number of I/O ports. So the number of I/O ports increases in going from lower to higher family members. Another obvious because of course higher family members are expensive. And then next is we have increasing memory size. The size of main memory increases in going from lower to higher family members, right? And then increasing cost, of course. At a given point in time, the cost of a system increases in going from lower to higher family members, and it will never be the other way around. So, how could such a family concept be implemented? Differences were achieved based on three factors: basic speed, size, and degree of simultaneity. So, for example, greater speed in the execution of a given instruction could be gained by the use of more complex circuitry and the ALU, allowing sub-operations to be carried out in parallel. Another way of increasing speed was to increase the width of the data path between main memory and the CPU. On the Model 30, only 1 byte or 8 bits could be fetched from main memory at a time, whereas 8 bytes could be fetched at a time on the Model 75. So that's why the difference between the price. Model 75 is expensive because it has a wider data path compared to Model 30. And then the System 360 not only dictated the future course of IBM, but also had a profound impact on the entire industry. Many of its features have become standard on other large computers. Okay, next is we have another. So aside from IBM System 360, we have another computer which is developed by Digital Equipment Corporation, which is the PDP-8. So in the same year that IBM shipped its first System 360, another momentous first shipment occurred. The PDP, or short for Programmed Data Processor, PDP-8 from Digital Equipment Corporation, or DEC. At the time, when the average computer required an air-conditioned room, the PDP-8, dubbed a mini computer by the industry after the miniskirt of the day, was small enough that it could be placed on top of a lab bench or be built on to another equipment. It could not do everything the mainframe could do, but $16,000 It was cheap enough for each lab technician to have one. So in contrast, the System 360 series of mainframe computers is introduced just a few months before, cost hundreds of thousands of dollars. So as you can have an idea of a mainframe computer, in those era, actually, there is also its system unit is already composed of one room, or its system unit is as large as a refrigerator. So that's as how big as it is and those times. But nowadays, the performance level of those computers can already be here in our laptops, which is of course smaller. Okay, then the low cost and small size of the PDP-8 enabled another manufacturer to purchase a PDP-8 and integrate it into a total system for resale. So these other manufacturers came to be known as original equipment manufacturers, or OEMs, and the OEM market became and remains a major segment of the computer marketplace. So in contrast to the central switch architecture, so with figure 1.9, used by IBM on its 700, 7000 series and 360 systems, so the later models of the PDP-8 use a structure that became virtually universal for microcomputers, the bus architecture. So this is the bus architecture. And of course, it is illustrated in this figure. So the PDP-8 bus, called the Omnibus, consists of 96 separate signal paths used to carry control, address, and data signals. Because all system components share a common set of signal paths, their use can be controlled by the CPU. So this architecture is highly flexible, allowing modules to be plugged into the bus to create various configurations. It is only in recent years that the bus structure has given way to a structure known as point-to-point interconnect, or P2P, as described in chapter 3. Okay, since we are already finished with the third generation, so how about the next generations, or it is already summarized as the later generations, the LSI, VLSI, and the ULSI. So beyond the third generation, there is less general agreement on defining generations of computers. So with table 1.2 suggests that there have been a number of later generations based on advances in integrated circuit technology. With the introduction of large-scale integration, or LSI, more than 1,000 components can be placed on a single integrated circuit chip, while the VLSI, or the Very Large Scale Integration, achieved more than 10,000 components per chip, while the Ultra, or the current Ultra Large Scale Integration, or the ULSI, chips can contain more than 1 billion components. With the rapid pace of technology, the high rate of introduction of new products, and the importance of software and communications as well as hardware, the classification by generation become less clear and less meaningful. So in this section, we mentioned the two of the most important developments in later generations. So first is we have the semiconductor memory. So the first application of integrated circuit technology to computers was the construction of the processor, which is composed of the control unit, the arithmetic and logic unit, out of integrated circuit chips, or the IC chips. But was also found that this same technology could be used to construct memory. So aside from ICs, we can make a processor by means of ICs. We can also create memories the foundation of components is the IC. So in the 1950s and 1960s, most computer memory was constructed from tiny rings of ferromagnetic material, each about a 16th of an inch in diameter. So these rings were strung up on grids of fine wire suspended on small screens inside the computer. So magnetized on one way, a ring, which is also called a core, represented a 1 magnetized, and the other way it stood for a 0. Magnetic core memory was rather fast. It took as little as a millionth of a second to read a bit stored in memory. But the problem is it was expensive, bulky, and used destructive readout. The simple act of reading a core erased the data stored in it. It was therefore necessary to install circuits to restore the data as soon as it had been extracted. Then in the 1970s, Fairchild produced the first relatively capacious semiconductor memory. This chip, about the size of a single core, could hold 256 bits of memory. It was non-destructive and much faster than the core. It took only 70 billionths of a second to read a bit. However, the cost per bit was higher than for that of the core. So that's the problem with this produced by Fairchild. It's very expensive. Then in 1974, a seminal event occurred. The price per bit of semiconductor memory dropped below the price per bit of core memory. Following this, there has been a continuing rapid decline in memory cost accompanied by a corresponding increase in physical memory density. This has led the way to smaller, faster machines with memory sizes of larger and more expensive machines from just a few years earlier. Developments in memory technology, together with developments in processor technology to be discussed next, changed the nature of computers in less than a decade. Although bulky, expensive computers remain part of the landscape, the computer has been brought out to the end user with office machines and personal computers. And then since 1970s, semiconductor memory has been through 13 generation. We have a 1 kilobyte, 4 kilobyte, 16 kilobyte, 64 kilobyte, 256 kilobyte, 1 megabyte, 4 megabyte, 16 megabytes, 64 megabytes, 256 megabytes, 1 gigabyte, 4 gigabytes, and as of this writing of this our lecture series, we have 8 gigabyte on a single chip. So as we can see, 1 kilobyte is equivalent to 2 raised to 10, and then 1 megabyte is roughly equal to 2 raised to 20, and 1 gigabyte is approximately equivalent to 2 raised to 30. Each generation has provided 4 times the storage density of the previous generation, accompanied by the declining cost per bit and declining access time. Densities are projected to reach 16 gigabyte by 2018 and 32 gigabyte by 2023. So aside from semiconductor memory is we have the microprocessors. Just as the density of elements on memory chips has continued to rise, so has the density of elements on processor chips. As time went on, more and more elements were placed on each chip, so that fewer and fewer chips were needed to construct a single computer processor. A breakthrough was achieved in 1971 when Intel developed its 4004. The 4004 was the first chip to contain all of the components of a CPU and a single chip, and thus the microprocessor was born. The 4004 can add two 4-bit numbers and can multiply only by repeated addition. By today's standards, the 4004 is hopelessly primitive or Jurassic, but it marked the beginning of a continuing evolution of microprocessor capability and power. So this evolution can be seen most easily in number of bits that the processor deals with at a time. There is no clear-cut measure of this, but perhaps the best measure is the data bus width, or the number of bits of data that can be brought into or sent out of the processor at a time. Another measure is the number of bits in the accumulator or in the set of general purpose registers. Often, these measures coincide, but not always. For example, a number of microprocessors were developed that operate on a 16-bit numbers in registers but can only read and write 8 bits at a time. So the next major step in the evolution of the microprocessor was the introduction in 1972 of the Intel 8008. This was the first 8-bit microprocessor and was almost twice as complex as the 4004. Neither of these steps was to have the impact of the next major event, the introduction in 1974 of the Intel 8080. This was the first general-purpose microprocessor. So Intel 8080 is considered the first general microprocessor, whereas the 4004 and the 8008 had been designed for specific applications. The 8080 was designed to be the CPU of a general-purpose microcomputer. Like the 8008, the 8080 is an 8-bit microprocessor. The 8080, however, compared with 8008 is faster, has richer instruction set, and has a large addressing capability. So that is why it is called the first general purpose microprocessor. So in the table is we have a summary of the 1970s processor, and we have the history and specifications. So about the same time, the 16-bit microprocessors began to be developed. However, it was not until the end of the 1970s that powerful, general-purpose 16-bit processors appeared. One of these was the 8086. The next step in this trend occurred in 1981 when both Bell Labs and the Hewlett-Packard developed 32-bit single-chip microprocessors. And also, Intel introduced its own 32-bit microprocessor, the 8386 in 1985. So we can see this um, in our the next tables. So this is the 1970 processors, and next is we have the 1980s. So for the 1980s, so we have the 8286, we have the 3860MDX, and then the 3860MSX, and the 4860MDX CPU. So always the trend is the transistors are the contents is more denser because more transistors, the clock speed is higher. Of course, it was the development of the processor is progressive. And then for the 1919 processors, we have the 4860MSX, the Pentium Pro, and then the Pentium 2. And then for the recent processors, we have the Pentium 3, Pentium 4, the Core 2 Duo, and the Core i7 EE49660X. So Core i7 is, as of now, the latest. So next is we have the evolution of the Intel x86 architecture. So throughout this book or our lecture series, we rely on many concrete examples of computer design and implementation to illustrate concepts and to eliminate trade-offs. Numerous systems, both contemporary and historical, provide examples of important computer architecture design features. But our lecture series relies principally on examples from two processor families. We have the Intel x86 and the ARM architecture. So we are going to have a separate discussion for ARM architecture. So the current x86 offerings represent the results of decades of design effort on complex instruction set computers, or the CISC or CISCs. So the x86 incorporates the sophisticated design principles once found only on mainframes and supercomputers and serves as an excellent example of CISC design. An alternative approach to processor design is the RISC instruction set computer, or the RISC or RISC. So the ARM architecture is used in a wide variety of embedded systems and is one of the most powerful and best designed RISC-based systems on the market. So to have a further information, ARM architecture is used on our mobile phones. In this section and the next, we provide a brief overview of these two systems. In terms of market share, Intel has ranked as the #1 maker of microprocessors for non-embedded systems for decades, a position it seems unlikely to yield. Up until now, it's still Intel. And then the evolution of its flagship microprocessor product serves as a good indicator of the evolution of computer technology in general. So the table previously shows that evolution. Interestingly, as microprocessors have grown faster and much more complex, Intel has actually picked up the pace. Intel used to develop microprocessors one after another every 4 years, but Intel hopes to keep rivals at bay by trimming a year or two off this development time, has done so with the most recent x86 generations. So, what are the highlights of the evolution of the Intel product line? So, it is worthwhile to list some of the highlights of the evolution of the Intel product line, such as with 8080, the world's first general purpose microprocessor. This was an 8-bit machine with an 8-bit data path to memory. The 8080 was used in the first personal computer, the Altair. And then next is we have the 8086, a far more powerful 16-bit machine. In addition to a wider data path and larger registers, the 8086 supported an instruction cache or queue that prefetches a few instructions before they are executed. A variant of this processor, which is the 8088, was used in IBM's first personal computer, securing the success of Intel. And then the 8086 is the first appearance of the x86 architecture. Next is we have the 8286. This extension of the 8086 enabled addressing a 16 megabyte memory instead of just 1 megabyte. And then next is we have the 8386, the Intel's first 32-bit machine and a major overhaul of the product. With the 32-bit architecture, the 8386 rivaled the complexity and power of mini computers and mainframes introduced just a few years earlier. This was the first Intel processor to support multitasking, meaning it could run multiple programs at the same time. And then we have the 8486. So the 8486 introduced the use of much more sophisticated and powerful cache technology and sophisticated instruction pipelining. The 8486 also offered a built-in math coprocessor, offloading complex math operations from the main CPU. As continuation of the evolution of the Intel product line, so Pentium, with the Pentium, Intel introduced the use of superscalar techniques, which allow multiple instructions to execute in parallel. It is called Pentium. Pen means 5 for pentagon. So Pentium, it should be 8586. So as you can recall, 8286, 8386, 8486. So Pentium actually is 8586. And then next continuation is we have the Pentium Pro. The Pentium Pro continued the move into superscalar organization begun with the Pentium, with aggressive use of register renaming, branch prediction, data flow analysis, and speculative execution. And then next is we have the Pentium 2. The Pentium 2 incorporated the Intel MMX technology, which is designed specifically to process video, audio, and graphics data efficiently. So MM means multimedia. And then Pentium 3, the Pentium 3 incorporates additional floating point instructions. The streaming SIMD extension or the SSE instruction set extension added 70 new instructions designed to increase performance when exactly the same operations are to be performed on multiple data objects. Typical applications are digital signal processing and graphics processing. And then we have the Pentium 4. The Pentium 4 includes additional floating point and other enhancements for multimedia. And then next is we have Core. This is the first Intel x86 microprocessor with a dual core, referring to the implementation of two cores on a single chip. As I have example, two brains inside your head, in our head. And then Core 2. The Core 2 extends the core architecture of 264-bit. The Core 2 Quad provides 4 cores on a single chip, so that's why it's quad. 4 cores on a single chip. More recent core offerings have up to 10 cores per chip. An important addition to the architecture was the advanced vector extensions instruction set that provided a set of 256-bit and then 512-bit instructions for efficient processing of vector data. So almost 40 years after its introduction in 1978, the x86 architecture continues to dominate the processor market outside of embedded systems. Although the organization and technology of the x86 machines have changed dramatically over the decades, the instruction set architecture has evolved to remain backward compatible with earlier versions. So that's why it's very lucky and considerate of Intel. Thus, any program written on an older version of the x86 architecture can execute on newer versions. But of course, newer versions of programs cannot be executed on older versions of the processor because of the limited transistors and also the speed and the data path. And then another is all changes to the instruction set architecture have involved additions to the instruction set with no subtractions. The rate of change has been the addition of roughly one instruction per month added to the architecture, so that there are now thousands of instructions in the instruction set. So also the x86 provides an excellent illustration of the advances in computer hardware over the past 35 years. The 1978 8086 was introduced with a clock speed of 5 MHz and had 29,000 transistors. A 6-core i7-EE4960X introduced in 2013 operates at 4 GHz, a speed up of a factor of 800, and has compared to 8086 of 1978, which has 29,000 transistors, it has 1.86 billion transistors, about 64 times as many as the 8086. Yet, the Core i7 EE4960X is in only a slightly larger package than the 8086 and has a comparable cost. So we already finished with the highlights of the evolution of the Intel product line. Next is we have the embedded systems. So the term embedded system refers to the use of electronics and software within a product as opposed to a general purpose computer such as a laptop or desktop system. Millions of computers are sold every year, including laptops, personal computers, workstations, servers, mainframes, and supercomputers. In contrast, billions of computer systems are produced each year that are embedded within larger devices. Today, many, perhaps most, devices that use electronic power have an embedded computing system. It is likely that in the near future, virtually all such devices will have embedded computing systems. So, are you wondering what are these devices? So, let's continue. Types of devices with embedded systems are almost too numerous to list. So, examples of these embedded systems include cell phones, digital cameras, video cameras, calculators, microwave ovens, home security systems, washing machines, lighting systems, thermostats, printers, various automated systems such as transmission control, cruise control, fuel injection, anti-lock brakes, and suspension systems, tennis rackets, toothbrushes, and numerous types of sensors and actuators in an automated system. So, embedded system, as long as it is digital and has a microprocessor, it is an embedded system with a specific purpose. So often, embedded systems are tightly coupled to their environment. This can give rise to real-time constraints imposed by the need to interact with the environment. Constraints such as required speeds of motion, required precision of measurement, and required time durations dictate the timing of software operations. If multiple activities must be managed simultaneously, this imposes more complex real-time constraints. So next is we have the figure of 1.14 possible organization of an embedded system. So by this figure, it shows in general terms an embedded system organization. In addition to the processor and memory, which is we have this, there are a number of elements that differ from the typical desktop or laptop computer. First is, there may be a variety of interfaces that enable the system to measure, manipulate, and otherwise interact with the external environment. Embedded systems often interact. What are these interactions? It can be sensing, manipulating, and communicate with external world through sensors and actuators, and hence are typically reactive systems. A reactive system is in continual interaction with the environment and executes at a pace determined by that environment. And then the human interface may be as simple as a flashing light or as complicated as real-time robotic vision. In many cases, there is no human interface. Next is diagnostic port. May be used for diagnosing the system that is being controlled, not just for diagnosing the computer. Then next is we have the special purpose field programmable or the FPGA, application specific ASIC, or even non-digital hardware may be used to increase performance or reliability. Software often has a fixed function and is specific to the application. And efficiency is of paramount importance for embedded systems. They are optimized for energy, code size, execution time, weight and dimensions, and cost. There are several noteworthy areas of similarity to general purpose computer systems as well, such as even with nominally fixed function software, the ability to field upgrade to fix bugs, to improve security, and to add functionality has become very important for embedded system and not just in consumer devices. So one comparatively recent development has been of embedded system platforms that support a wide variety of apps. Good examples of this are smartphones, as what we are using now, and then the audiovisual devices such as smart TVs. So another thing or another term that has emerged nowadays is the called Internet of Things or the IoT. It is worthwhile calling out separately one of the major drivers in the proliferation of embedded systems. The Internet of Things or IoT is a term That refers to the expanding interconnection of smart devices ranging from appliances to tiny sensors. A dominant theme is the embedding of short-range mobile transceivers into a wide array of gadgets and everyday items, enabling new forms of communication between people and things, and between things themselves. The internet now supports the interconnections of billions of industrial and personal objects, usually through cloud systems. The objects deliver sensor information, act on their environment, and in some cases, modify themselves to create overall management of a larger system like a factory or a city rather. The IoT is primarily driven by deeply embedded devices. These devices are low bandwidth, so the definition of deeply embedded devices: low bandwidth, low repetition data capture, and low bandwidth data usage appliances that communicate with each other and provide data via user interfaces. Embedded appliances such as high resolution video security cameras, video VoIP or voice over IP phones, and a handful of others require high bandwidth streaming capabilities. Yet, countless products simply require packets of data to be intermittently delivered. With reference to the end system supported, the Internet has gone through roughly 4 generations of deployment culminating in the IoT. First is information technology or IT. PCs, servers, routers, firewalls, and so on, bought as IT devices by enterprise IT people and primarily using wired connectivity. Next is operational technology or OT. Machines or appliances with embedded IT built by non-IT companies such as medical machinery, SCADA, or supervisory control and data acquisition, process control, and kiosk, both as appliances by enterprise OT people and primarily using wired connectivity. And we have personal technology such as smartphones, tablets, and e-book readers bought as IT devices by consumers or employees exclusively using wireless connectivity and often multiple forms of wireless connectivity. And then we have sensor or actuator technology, single purpose devices bought by consumers, IT and OT people exclusively using wireless connectivity, generally of a single form as part of larger systems. It is the fourth generation that is usually thought of as the IoT and is marked by the use of billions of embedded devices. Another example of an IoT appliance is, for example, is you have a ref in which, for example, you have already less inventory of eggs. Um, if you have set up its ability, for example, since you set up that there is, or if there is no eggs anymore in the refrigerator, the ref can order online to replenish your inventory of eggs. That is also an example of IoT. Okay, so next is we have the differences or discussion between embedded operating systems and application processors versus dedicated processors. There are two general approaches to developing an embedded operating system. The first approach is to take an existing OS and adapt it for the embedded application. For example, there are embedded versions of Linux, Windows, and Mac, as well as other commercial and proprietary operating systems specialized for embedded system. The other approach is to design and implement an OS intended solely for embedded use. So an example of the latter is the Tiny OS, widely used in wireless sensor networks. And then in this subsection and the next two, we briefly introduce some terms commonly found in the literature and embedded systems. We have the application processors are defined by the processor's ability to execute complex operating systems such as Linux, Android, and Chrome. Thus, the application processor is general purpose in nature. And then also a good example of the use of an embedded application processor is the smartphone. And then the embedded system is designed to support numerous apps and perform a wide variety of functions, as we can already see and we're already doing in our smartphones. Smartphones is not only used for calling and texting, but you can already virtually use for anything, for gaming, for music, and others. So most embedded systems employ, in opposite of the general purpose embedded application processor, is we have the dedicated processor, which, as the name implies, is dedicated to one or a small number of specific tasks required by the host device. Because such an embedded device is dedicated to specific task or tasks, the processor and associated components can be engineered to reduce size and cost because it has only one function. So that's why it is reduced in size and in cost. So next is we have this figure 1.15, the typical microcontroller chip elements. So as we have seen, early microprocessor chips included registers, an ALU, and some sort of control unit or instruction processing logic. As transistor density increased, it became possible to increase the complexity of the instruction set architecture and ultimately to add memory and more than one processor. Contemporary microprocessor chips, as shown in figure 1.2, include multiple cores and a substantial amount of cache memory. So next is we have this microcontroller chip makes a substantially different use of the logic space available. So based on the figure shows, in general terms, the elements typically found in a microcontroller chip. As we can see, a microcontroller is a single chip that contains the processor, non-volatile memory for the program or ROM, volatile memory for input and output, which is the RAM, a clock, and an I/O control unit. The processor portion of the microcontroller has a much lower silicon area than other microprocessor and much higher energy efficiency. And then we will also have this discussion of microcontroller organization. And then also called, the microcontroller is also called a computer on chip. Billions of microcontroller units are embedded each year in myriad products from toys to appliances to automobiles. For example, a single vehicle can use 70 or more microcontrollers. Typically, especially for the smaller, less expensive microcontrollers, they are used as dedicated processors for specific tasks. For example, microcontrollers are heavily utilized in automation processes. By providing simple reactions to input, they can control machinery, turn fans on and off, open and close valves, and so forth. They are integral parts of modern industrial technology and are among the most inexpensive ways to produce machinery that can handle extremely complex functionalities. So why is it inexpensive? Because there are already microcontrollers that are open source and it really costs low, such as the Arduino microcontroller. Microcontrollers come in a range of physical sizes and processing power. Processors range from 4-bit to 32-bit architectures. Microcontrollers tend to be much lower than microprocessors, typically operating in the megahertz range rather than the gigahertz speeds of microprocessors because, of course, these only serve a specific purpose. Another typical feature of a microcontroller is that it does not provide for human interaction. The microcontroller is programmed for a specific task, as I've said, embedded in its device, and executes as and when required. Okay, next is we have another, as already mentioned, we have the deeply embedded systems. We have in this section defined the concept of an embedded system. A subset of embedded system and a quite numerous subset is referred to as deeply embedded systems. Although this term is widely used in the technical and commercial literature, and then if we're going to search in the internet, we are in vain, or if you're going to try for a straightforward definition. Generally, we can say that a deeply embedded system has a processor whose behavior is difficult to observe both by the programmer and the user. A deeply embedded system uses a microcontroller rather than a microprocessor, is not programmable once the program logic for the device has been burned into ROM or the read-only memory, and has no interaction with the user. Deeply embedded systems are dedicated, single-purpose devices that detect something in the environment, perform a basic level of processing, and then do something with the results. Deeply embedded systems often have wireless capability and appear in network configurations, such as networks of sensors deployed over a large area, such as factory, agricultural field. The Internet of Things depends heavily on deeply embedded systems. Typically, deeply embedded systems have extreme resource constraints in terms of memory, processor size, time, and power consumption. Okay, next is we have the ARM. So ARM, or ARM stands for Advanced Risk Machines. And actually, it is originally known as the Acorn Risk Machine. So the ARM architecture refers to a processor architecture that has evolved from RISC design principles and is used in embedded system. So in chapter 15 examines the RISC design principles in detail. In this section, we give a brief overview of the ARM architecture. So ARM or ARM is a family of RISC-based microprocessors and microcontrollers designed by ARM Holdings, Cambridge, England. The company doesn't make processors but instead designs microprocessor and multi-core architectures and licenses them to manufacturers. Specifically, ARM Holdings has two types of licensable products, the processor and processor architectures. For processors, the customer buys the rights to use ARM supplied design in their own chips. For a processor architecture, the customer buys the rights to design their own processor compliant with ARM's architecture. ARM chips are high-speed processors that are known for their small die size and lower power requirements. They are widely used in smartphones and other handheld devices, including game systems, as well as a large variety of consumer products. So these are prevalent ARM architectures or processors in our smartphones and other handheld devices. ARM chips are the processors in Apple's popular iPad and iPhone devices and are used in virtually all Android smartphones as well. ARM is probably the most widely used embedded processor architecture and indeed the most widely used processor architecture of any kind in the world. The origins of ARM technology can be traced back to the British-based Acorn Computers Company. In the early 1980s, Acorn was awarded a contract by the British Broadcasting Corporation or BBC to develop a new microcomputer architecture for the BBC Computer Literacy Project. The success of this contract enabled Acorn to go on to develop the first commercial RISC processor, the Acorn RISC machine or the ARM, the original name for ARM. The first version, ARM1, became operational in 1985 and was used for internal research and development as well as being used as a coprocessor in the BBC machine. In this early stage, Acorn used company VLSI technology to do the actual fabrication of the processor chips. VLSI was licensed to market the chip on its own and has some success in getting other companies to use the ARM in their products, particularly as an embedded processor. The ARM design matched a growing commercial need for a high performance, low power consumption, small size, and low cost processor for embedded applications. But further development was beyond the scope of Acorn's capabilities. Accordingly, a new company was organized with Acorn, VLSI, and Apple Computer as founding partners, known as ARM Ltd or Limited. So the Acorn RISC machine became Advanced RISC Machine. So next is we have the ARM products. So ARM Holdings licenses a number of specialized microprocessors and related technologies, but the bulk of their product line is the Cortex family of microprocessor architectures. There are three Cortex architectures, conveniently labeled with the initials A, R, and M. So first is we have the Cortex A and Cortex A50 are application processors intended for mobile devices such as smartphones and e-book readers, as well as consumer devices such as digital TV and home gateways such as DSL and cable internet modems. So these processors run at higher clock frequency over 1 gigahertz and support a memory management unit or MMU, which is required for full feature OSs such as Linux, Android, MS Windows, or mobile OSs. An MMU is a hardware module that supports virtual memory and paging by translating virtual addresses into physical addresses. So this topic is also explored in Chapter 8. So the two architectures use both the ARM and Thumb 2 instruction sets. The principal difference is that the Cortex-A is a 32-bit machine and the Cortex-A50 is a 64-bit machine. So next is we have the Cortex-R. It is designed to support a real-time applications in which the timing of events needs to be controlled with rapid response to events. They can run at a fairly high clock frequency such as 200 megahertz to 800 megahertz and have a very low response latency. It is lower than Cortex-A, but of course, it is since Cortex A is application processor, and it is used for mobile devices. As well, Cortex-R is specifically for real-time application, so that's why it's called Cortex-R. And then the Cortex-R includes enhancements both to the instruction set and to the processor organization to support deeply embedded real-time devices. Most of these processors do not have MMU. The limited data requirements and the limited number of simultaneous processes eliminates the need for elaborate hardware and software support for virtual memory. The Cortex-R does have a memory protection unit, cache, and other memory features designed for industrial applications. So an MPU, or the Memory Protection Unit, is a hardware module that prohibits one program in memory from accidentally accessing memory assigned to another active program. Using various methods, a protective boundary is created around the program, and instructions within the program are prohibited from referencing data outside of that boundary. Examples of embedded systems that would use the Cortex-R are automotive braking systems, mass storage controllers, and networking and printing devices. So the devices that uses Cortex-R have very specific purposes. Next is we have the Cortex-M. These are the series of processors that have been developed primarily for the microcontroller domain, where the need for fast, highly deterministic interrupt management is coupled with the desire for extremely low gate count and lowest possible power consumption. As with the Cortex-R series, the Cortex-M architecture has an MPU but no MMU. The Cortex-M uses only the Thumb 2 instruction set. The market for the Cortex-M includes IoT devices, wireless sensor or actuator networks used in factories and other enterprises, automotive body electronics, and so on. There are currently four versions of the Cortex M series, which is the Cortex M0. So this is designed for 8 and 16-bit applications. This model emphasizes low cost, ultra low power, and simplicity. It is optimized for small silicon die size starting from 12,000 gates and used in lowest cost chips. Then next is we have the Cortex M0 Plus, an enhanced version of the M0 that is more energy efficient. Next is we have the Cortex M3, designed for 16 and 32-bit applications. This model emphasizes performance and energy efficiency. It also has comprehensive debug and trace features to enable software developers to develop their applications quickly. And then last but not the least is we have the Cortex M4. So this model provides all the features of the Cortex M3 with additional instructions to support digital signal processing tasks. So in this lesson, we will primarily use the ARM Cortex M3 as our example embedded system processor. It is the best suited of all ARM models for general purpose microcontroller use. The Cortex M3 is used by a variety of manufacturers of microcontroller products. Initial microcontroller devices from lead partners already combined the Cortex M3 processor with flash, SRAM, and multiple peripherals to provide a competitive offering at the price of just $1. Okay, next is we have the figure of a typical microcontroller chip based on Cortex M3. So this figure provides a block diagram of the EFM32 microcontroller from Silicon Labs. The figure also shows detail of the Cortex M3 processor. So we have this one, and then the core and its core components. So we examine each level in turn. So the M3, or the Cortex M3 core, makes use of separate buses for instructions and data. And then this arrangement is sometimes referred to as a Harvard architecture, in contrast with the von Neumann architecture, which uses the same signal buses and memory for both instructions and data. By being able to read both an instruction and data from memory at the same time, the Cortex M3 processor can perform many operations in parallel, speeding application execution. The core contains a decoder for thumb instructions, an advanced ALU with support for hardware multiply and divide, control logic, and interfaces to the other components of the processor. In particular, there is an interface to the Nested Vector Interrupt Controller, or the NVIC, and the Embedded Trace Macrocell, or the ETM module. The core part is part of the module called the Cortex M3 processor. This term is somewhat misleading because typically in the literature, the terms core and processor are viewed as equivalent. In addition to the core, the processor includes the following elements: the NVIC. We have this one, the core of the Cortex M3, so provides a considerable interrupt handling abilities to the processor. It facilitates low latency exception and interrupt handling and controls power management. Next is we have the ETM, an optional debug component that enables reconstruction of program execution. The ETM is designed to be a high-speed, low-power debug tool that only supports instruction trace. Next is we have Debug Access Port or DAP. This provides an interface for external debug access to the processor. Next is we have the Debug Logic. Basic debug functionality includes processor halt, single-step processor core register access, unlimited software breakpoints, and full system memory access. Next is we have the iCode interface. Fetches instructions from the code memory space, SRAM and peripheral interface, read or write interface to data, memory, and peripheral devices. Next is we have the bus matrix, connects the core and the debug interfaces to external buses on the microcontroller. Next is memory protection unit, protects critical data used by the operating system from user applications, separating processing tasks by disallowing access to each other's data, disabling access to memory regions, allowing memory regions to be defined as read-only, and detecting unexpected memory accesses that could potentially break the system. The upper part of the figure shows the block diagram of a typical microcontroller built with the Cortex M3, in this case the EFM3 microcontroller. So this is the microcontroller chip. So this microcontroller is marketed for use in a wide variety of devices including energy, gas and water metering, alarm and security systems, industrial automation devices, home automation devices, smart accessories, and health and fitness devices. The silicon chip rather consists of 10 main areas such as core and memory. So this region includes the Cortex M3 processor, the static RAM or the SRAM, data memory and flash memory for storing program instructions, and non-variating application data. Flash memory is non-volatile, which is the term na data is not lost when the power is shut off, and so is ideal for this purpose. The SRAM stores variable data. This area also includes a debug interface, which make it easy to reprogram and update the system in the field. Next is we have the parallel I/O ports. So these are configurable for a variety of parallel I/O schemes. And then if we have parallel, we also have serial interfaces. Supports various serial I/O schemes. And then next is we have analog interfaces, analog to digital and digital to analog logic to support sensors and actuators. Next is timers and triggers, keeps track of timing and count events, generates output waveforms, and triggers timed actions in other peripherals. Next is clock management, controls the clocks and oscillators on the chip. Multiple clocks and oscillators are used to minimize power consumption and provides short startup times. Next is we have the energy management, manages various low energy modes of operation of the processor and peripherals to provide real-time management of the energy needs so as to minimize energy consumption. Next is security. The chip includes a hardware implementation of an advanced encryption standard. This standard is used for wireless connections. Then next is we have the 32-bit bus. Connects all of the components on the chip. Peripheral bus, a network which lets the different peripheral module communicate directly with each other without involving the processor. This supports timing critical operation and reduces software overhead. Comparing figure 1.16 with figure 1.2, we may see many similarities and the same general hierarchical structure. Note, however, that the top level of a microcontroller computer system is a single chip, whereas for a multi-core computer, the top level is a motherboard containing a number of chips. Another noteworthy difference is that there is no cache. As you can see, there's no cache with this with microcontroller chip. neither in the Cortex M3 processor nor in the microcontroller as a whole, which plays an important role if the code or data resides in external memory. Though the number of cycles to read the instruction or data varies depending on cache hit or miss, the cache greatly improves the performance when external memory is used. Such overhead is not needed for a microcontroller. So aside from microcontroller is we have cloud computing. So although the general concepts for cloud computing go back to the 1950s, cloud computing services first became available in the early 2000s, particularly targeted at large enterprises. Since then, cloud computing has spread to small and medium-sized businesses and most recently to consumer. Apple's iCloud was launched in 2012 and had 20 million users within a week of launch. Evernote, the cloud-based note-taking and archiving service, launched in 2008, approached 100 million users in less than 6 years. So in this section, we provide a brief overview, and cloud computing is also examined in more detail in Chapter 17. There is an increasingly prominent trend in many organizations to move a substantial portion or even all information technology operations to an internet-connected infrastructure known as enterprise cloud computing. At the same time, individual users of PCs and mobile devices are relying more and more on cloud computing services to back up data, sync devices, and share using personal cloud computing. NIST defines cloud computing as follows. So, cloud computing, a model for enabling ubiquitous, convenient, on-demand network access to a shared pool of configurable computing resources such as networks, servers, storage, applications, and services that can be rapidly provisioned and released with minimal management effort or service provider interaction. Basically, with cloud computing, you get economies of scale rather, professional network management, and professional security management. These features can be attractive to companies large and small, government agencies, and individual PC and mobile users. The individual or company only needs to pay for the storage capacity and services they need. The user, be it company or individual, doesn't have the hassle of setting up a database system, acquiring the hardware they need, doing maintenance, and backing up the data. All these are part of the cloud service. In theory, another big advantage of using cloud computing to store your data and share it with others is that the cloud provider takes care of security. Alas, the computer is not always protected, or rather, the customer. There have been a number of security failures among cloud providers. Evernote made headlines in early 2013 when it told all of its users to reset their passwords after an intrusion was discovered. So, an application of cloud computing is what we're using, Facebook or any other online services in Google. So, cloud computing for Facebook, if I may ask you, do you know what specific computer location is your data stored in Facebook? Of course, we do not know it. It's just there in the servers. So that is already an example of a cloud computing. So next, further detail of the discussion of cloud computing is we have also the cloud networking. So cloud networking refers to the networks and network management functionality that must be in place to enable cloud computing. Most cloud computing solutions rely on the internet, of course, but that is only a piece of the networking infrastructure. One example of cloud networking is the provisioning of high performance and or high reliability networking between the provider and subscriber. In this case, some or all of the traffic between an enterprise and the cloud bypasses the internet and uses dedicated private network facilities owned or leased by the cloud service provider. More generally, cloud networking refers to the collection of network capabilities that are required to access a cloud, including making use of specialized services over the internet, linking enterprise data centers to a cloud, using firewalls and other network security devices at critical points to enforce access security policies. So we can think, so we have cloud networking and then we have the cloud storage as a subset of cloud computing. In essence, cloud storage consists of database storage and database applications hosted remotely on cloud servers. Cloud storage enables small businesses and individual users to take advantage of data storage that scales with their needs and to take advantage of a variety of database applications without having to buy, maintain, and manage the storage assets. So the next figure is we have in figure 1.17, the alternative information technology architectures. So the essential purpose of cloud computing is to provide for the convenient rental of computing resources. A cloud service provider, or the CSP, maintains computing and data storage resources that are available over the internet or private networks. Customers can rent a portion of these resources as needed. Virtually all cloud services are provided using one of the three models. We have the SaaS, PaaS, and IaaS, which we examined in this section. So first is we have the SaaS. So SaaS, or software as a service, as the name implies, SaaS cloud provides service to customers in the form of software, specifically application software running on and accessible in the cloud. SaaS follow the familiar model of web services, in this case applied to cloud resources. SaaS enables the user to use the cloud provider's applications running on the provider's cloud infrastructure. The applications are accessible from various client devices through a simple interface such as a web browser. Instead of obtaining desktop and server licenses for software product it uses, an enterprise obtains the same functions from the cloud service. SaaS saves the complexity of software installation, maintenance, and upgrades and patches. Examples of services of SaaS are Gmail, Google's email services, and Salesforce.com, which helps firms keep track of their customers. Common subscribers to SaaS are organizations that want to provide their employees with access to typical office productivity software such as document management and email. Individuals also commonly use the SaaS model to acquire cloud resources. Typically, subscribers use specific applications on demand. The cloud provider also usually offers data-related features such as automatic backup and data sharing between subscribers. So we're finished with SaaS. Next is we have PaaS, or Platform as a Service. A PaaS cloud provides service to customers in the form of a platform on which the customer's applications can run. PaaS enables the customer to deploy onto the cloud infrastructure containing customer-created or acquired applications. A PaaS cloud provides useful software building blocks, plus a number of development tools such as programming languages, runtime environments, and other tools that assist in deploying new applications. In effect, PaaS is an operating system in the cloud. PaaS is useful for an organization that wants to develop new or tailored applications while paying for the needed computing resources only as needed and only for as long as needed. Google App Engine and Salesforce platform from Salesforce.com are examples of PaaS. So next is we have the infrastructure as a service, or the IaaS. With IaaS, the customer has access to the underlying cloud infrastructure. IaaS provides virtual machines and other abstracted hardware and operating systems which may be controlled through a service application programming interface, or API. IaaS offers the customer processing, storage networks, and other fundamental computing resources so that the customer is able to deploy and run arbitrary software, which can include operating systems and applications. IaaS enable customers to combine basic computing services such as number crunching and data storage to build highly adaptable computer systems. Examples of IaaS are Amazon Elastic Compute Cloud, or Amazon EC2, and Windows Azure. So these are the three types of um, service that are offered in the cloud compared with our traditional IT architecture. So for the summary of chapter 1, so what we have learned in chapter 1 is all about organization and architecture, structure and function, brief history of computers for the first generation, which uses vacuum tubes, the second generation used transistors, and the third generation used integrated circuits, and later generations that is based on integrated circuits for the third generation. Next is the evolution of the Intel x86 architecture. Then we have cloud computing, the basic concepts in cloud services, and then embedded systems such as Internet of Things, embedded operating systems, application processors versus dedicated processors, microprocessors versus microcontrollers, embedded versus deeply embedded systems. And then we also have ARM architecture. We have the overview of the ARM evolution, instruction set architecture, and ARM products. So I hope that you've learned something here in chapter 1. So I hope that you already have an overview of the computer organization and architecture. And then if you do enjoy and if you've learned something from this lesson, so please don't forget to like and subscribe my channel. So thank you very much. Good day and stay safe.